Johannes, now the floor is yours.
Thanks. Thanks a lot, Celine. Yeah, so I'm following very neatly to the work in Ecole in a very similar way, also with a slightly different angle. So I think it's very complementary. The paper I'm presenting is entitled also looking at inequality within countries in this case, and also including the impact dimension. And we use this in a kind of country level RISE model that we have been developed. Maybe I don't need to repeat the literature here, just saying that the model that we are using is this what we call the RISE 50 plus, which we've been working on over the last 2 or 3 years, which started basic on DICE 2016. So it comes more from the cost benefit integrated assessment models, and the main feature is that it kind of has most country level detail, in that we feature 57 countries/regions. So the idea was to capture the highest level of national detail wherever we find especially mitigation cost functions available, and this happens to be 57, for which Enadata provides MAC curves, so we can replicate the mitigation cost across countries, which is important, of course, for mitigation. Yeah, so just we published a study earlier this year just at the global results, showing that basically, yeah, using this model and updated damage functions, basically we find that different from DICE 2013 or 16, that 1.5 to 2 degrees here are kind of the optimal scenarios. So that is the global result when you just use this country level version of RISE. Now here, what we did is basically we add to this model a complete new module which replicates country within country inequality. And we also added impacts, because we do also allow cost benefit analysis. And for that, the first thing we had to do is we were implementing a variety of different damage functions, which are out here. Here I just show basically the results of the different damage functions, I think 7 or so, that we've been implementing. And we see this wide range we had for the previous study, we used Berkey et al. In Nature, which was a famous study, also partly criticized for maybe not econometrically fully correct. So for this work, we use a more recent version of this climate econometric damage function, which is by Matthias Kalkul and Leonie Vance last year, who have been published it, who have an impact function which leads, if you here look in 2100, what are the global impacts at the macro level, to around 8% of GDP loss in a BAU. So this is kind of much less than the Dell et al. And Berkey et al. Functions that some people have been used or that have been discussed. So I think there's also a bit a convergence, one could say, to intermediate levels of damages, whereas these ones might have been a bit too high. But okay, we don't go too much into detail, just saying that for this work, in terms of impacts, we follow this specification, which could be considered an intermediate impact function. Now, when it comes to inequality, the main time that we spent on this work, which is also, I have to say, a work in progress, was first to get a good calibration of the current full income distribution of across individuals, both within countries and between countries. And then we add, similar to Nicolas just presented, carbon tax and distribution or mitigation effort by deciles. So the whole model we run on deciles. We don't use indices, but deciles in each country. And we also have damages, which are also, I come to that in a bit. And yeah, we compute basically. So the first step was to create this inequality scenarios for the SSPs, which I will spend some time on. And then we have a government budget, which also then has transfers, also similar to what we just presented, in that carbon tax transfers are transferred. And we have 3 different distribution schemes: a distributional neutral, an equal per capita basis, just like you presented. And we also have an optimal one, in which the social planner has as an additional control variable these transfers. And we run several scenarios. I will focus just on a very few here because of the limit of time. Yeah, so to start with, we wanted to really replicate the full income distribution that, for instance, people like Branko Milanovic have been writing about what they call the so-called concept 3, that is the full income distribution across all individuals at the globe. And here the latest official estimate is a Gini of 0.63 in 2011. And we try to get all the data from historical sources and from scenarios to replicate, let's say, income distributions at the global level to mimic the historical and combine it with projection data. So this is the way how we do it. We also use the projection by Rao et al. For our baseline projection. And so now I will just present, let's say, the first results and then some on inequality. So these are the scenarios. So we look at the cost-benefit an optimization, where basically we take into account this welfare function, which now has also inequality aversion, a $30 and a $100 carbon tax, both increasing at 5%, and the baseline. And this is basically, the temperature pathways. So we get to around 2 to 2.5 degrees because of the lower impact functions compared to Berkeley. But we also see a difference in terms of the different transfer schemes. We see that with an optimal transfer scheme, we lower the temperature even more. We do even more mitigation, and this has to do with the fact that, well, you use kind of revenue as a poverty and inequality reducing policy, and this makes carbon tax revenues worthy, and therefore this effect is not even small. You can see up to, let's say, 0.2 degrees. Just showing that there's a strong interaction effect between inequality and climate. How does inequality in this model affect the different deciles? So here you see the global income distribution. These are global deciles from 1 to 10. And we have basically 5 channels. So from a baseline which is just a baseline inequality projection, this is 2100, 2100 on the right and 2050 here. We have the mitigation costs in black. So this is basically what each decile pays according to an elasticity, which is based on a study by Budolfsson et al. That was just published 2 days ago on how these link to the deciles. Then we have damages in red. And they, of course, accrue also to an elasticity here. And finally, we have carbon tax. So the first one is really the mitigation action. And then we have the paid carbon tax. And this is transferred back. And we see especially that the transfers here in the optimal run can have an optimal effect, it can increase the lower deciles depending on the size and on the carbon tax. For instance, this is India, which has a much higher level of inequality, and you can see that here the lower deciles really can benefit from carbon transfers compared to the baseline. So how does then this whole different scenarios look out in terms of the global income distribution? So this is the global, this concept 3 Gini index, around a bit below 0.6 as of today. So relatively high level of inequality, but has been down from around 0.7 or a bit below over the last 15 years. And we see that in SSP2, this projection is continuing. So this is well based in the assumptions, and with impacts you have the red one. So you have a higher by around 3 points on the Gini, higher impacts due to climate change impacts. The black one would have been the reference. So already here the first result is that, well, climate impacts seem to be regressive at the global level and can indeed lead to, 3 points on the Gini is around twice the effect on COVID that had on inequality, which is estimated about 1.5 points. And in green, we have then the $30 carbon tax, which is a kind of intermediate policy, which to a different extent reduces these impacts. So basically, you see it's higher inequality than in the baseline without impacts, because, well, energy expenditure are typically regressive, or let's say that the taxation leads to an increase in inequality, but the transfer then can further reduce it. Especially with optimal transfers, we can see here that very early on, when carbon tax revenues are highest, there's a huge potential to reducing poverty, inequality, if transfer were really targeted at the lowest decile or 2. We also do it for the other SSPs. I will just maybe skip these graphs. Just maybe one last comment I want to make is that is the main part of within and between country inequality. I think that's a big policy issue. Piketty and others have written a lot about. And so what we did here is we decompose inequality in the 5 SSPs. So these are just the baselines here. And so the top line is total inequality. Here we use the tile index, which is the only one that is kind of decomposable without residual. And the solid parts are the within country inequality. And here what we see is that the SSPs prescribe some very strong convergence, especially in SSP 1 and 5, but also 2, where basically within country inequality really gets kind of marginalized by the end of the century almost. But what we found is that if we combine this with within country inequality, basically within country inequality is going to stay in especially SSP2 even increase, and in SSP3 and 4 even increase a lot. And if you look at this, yes, thanks. If you look at this just at the share, so this is the share of between and within country inequality, basically we see that within country inequality is gonna most likely dominate total global inequality by reaching over 80% in issues, including SSP2, meaning that, well, inequality is here to stay, that is for sure, but it seems that even more it's going to shift towards within country inequality. And this is just saying that I think this within country inequality is really important to capture, including in long-term topics such as climate change. If you look at just to the very end, for instance, the Lorenz curve at the very end of the century in these 5 SSPs, we see in black the current one, and then the 5 SSPs, and we see especially at the lower end that several SSPs are actually far out, meaning that there's higher level of inequality, especially at the bottom of the distribution, and only in the SSP1 and 5 with very optimistic values, inequality at the global level, total level is expected to decrease. Yeah, we could also look at who wins and loses of climate policy, but I'm sorry, we are out of time. So maybe just to take the main takeaway message, there is a lot of convergence at the macro level, but within country inequality is strong, and we found it to even increase to very high level, and it's an important thing to tackle. We see that redistribution can really reduce inequality and especially mitigate the impacts of climate change on inequality, and that is crucial. And especially per capita distribution, but even more targeted transfer to lower households might be even worthwhile. I'm sorry if I was a bit late, but it's a challenging time. With that, thanks very much, and looking forward if there's any question.
Thank you very much, Johannes. I think Hélène Benveniste has a question.
Yeah, thanks a lot, Johannes. Really super interesting presentation. I have just a couple questions. One was whether you could say a little more about how the kind of elasticities you use to distribute damages onto the different income levels, to what extent they're empirically grounded, and if they are, please let me know how you can do that, because I haven't been able to find any. And the other is, I'm just a little bit surprised by your main takeaway here, your first point on this slide, meaning that within country inequality would still very likely rise. I don't know if it's actually part of this work or actually it goes back to Narasimha's projections, because if you look at the qualitative narratives of the SSPs, you're supposed to see not just convergence between countries, but also perhaps decreases inequality also within countries, at least in a couple of narratives. So I'm just wondering whether you could comment on that. Thanks.
Yeah, thanks, Hélène. Both good questions. The first one on the elasticity. So yeah, we lose an elasticity of 0.5. There are some papers that have been using it, but indeed, that's actually the only parameter that we did not calibrate as of yet. So that's why in some other works we try to estimate these kind of impact functions on inequality by decile, and this is just showing some results on that, which is just under review, where we basically really look at deciles, how deciles are affected by climate change to calibrate this elasticity, which is just 0.5, which I think, yeah, empirically it's kind of in between 0 and 1, which are the ones which are the extreme ones. So that's, yeah, as of now not yet fully calibrated. The second part, yeah, I mean, that's of course, I mean, we calibrate the baseline mostly to historical data, and then the genies to Narasimha's paper. The point is, yeah, from their projection, it varies by country a lot. So indeed, there is some convergence scenarios, but even in those scenarios, in some countries you find divergence because of all countries are very different from our reading of the data. So when we do the aggregation at the global level, which is it's a lot of data crunching, we were also surprised to find these high levels. But it's also, I mean, understandable, I think, in policy terms that, well, convergence is strong, but inequality, especially at the very high, but also the very low distribution, is increasing across the world empirically. So in the end, it's not so surprising. But yeah, I mean, the baseline assumption is basically based on theirs. So yeah, I think it's something still to be seen and, yeah, also verified, and we can discuss happy, but it's based on their original works, basically.
Thank you very much. We go on with the third presentation now by Jarmo, I think.
Yeah, thanks a lot. I'll then tag on to Johannes's presentation and integrating also working more on some of Nicolas's work, but then look at a bottom-up perspective and build on a bottom-up understanding of inequality and the energy needs that are implied by this. So what's on the agenda? I'll first introduce a bit the decent living framework for those that are unfamiliar to it. Then talk about the global deprivations for those decent living standards that we define. Then look at the energy gaps and needs for providing a decent life to everyone. And then using these insights for future modeling, what can be learned from it perhaps. So the introduction, basically we look at this as a dual challenge of mitigation and development. This is what we're all doing, but developing scenarios for these pathways is still a big challenge. So one way we think that we can do this would be to start by defining material needs of well-being to basically cover this development aspect. Our way of doing this that I'm presenting here is by defining decent living standards, calculating the energy needs of those decent living standards, and then eventually feeding that back into integrated assessment modeling to be able to assess the environmental impacts. And in this presentation, I focus on the first three steps and not on the fourth yet. So what do I mean when I say what is a decent life? What are decent living standards? The decent living standards are basically material conditions for achieving a basic human well-being. So it's about the capacity to achieve something. And a decent life in our specification includes both needs on the household level, so it's heating, cooling, food, etc. On the community level, so also transport and education and healthcare, and as well then the societal infrastructures that are required for this, so road, electricity, and the production of these materials. And so for each of these need groups, so shelter, nutrition, health and hygiene, socialization, and mobility, we have the subdimensions and the material satisfiers for this. So enough floor space, enough water, etc. And we set certain thresholds for that. Based on these thresholds, then we can start collecting data and look at who has a decent life, or try to estimate who has a decent life. And this is basically combining a lot of poverty knowledge that is already there, just empirical data on, for instance, how many people live in slums, don't have good housing, or don't have access to clean cooking fuels, or lack proper sanitation. And so it's just combining basically World Bank, household surveys, and IPUMS and FAO data, and a couple of other sources. And then you got basically into a big picture of multidimensional inequality. And so I just put it on here. I'm not going to focus too much on it, but obviously the biggest gaps for most of these dimensions, so more than half of the dimensions in sub-Saharan Africa, more than half of the population actually lives below these decent living thresholds. And also South Asia is very poor. We know this, but basically now we have a data set for 2015 then. This is only 2015, to start building on. We have a starting point for bottom-up inequality. Then we go on to the question, how much energy is then needed to provide a decent life to everyone and to those that currently have it and don't have it. So the methods that we use here are multiple. Basically, we use a simulation model for buildings. We use multi-regional input-output tables and life cycle assessment for the other sectors. And with that, I can go more into detail if there are questions. With that, we basically calculate how much energy would be required to build out new stuff. So for all those that lacked decent living standards at the moment, we basically started looking at constructing all of this new energy. So it's only construction. And that is not that much compared to current energy use. So it's like, if we would provide everyone with decent living standards by 2040, the order of magnitude of rolling this out, the extra energy use that would be required is less than about 3% of current energy use. This is dominated by building new houses in sub-Saharan Africa and South Asia. In total, by about 2050, if everyone has decent living standards, the total energy need for providing decent living standards to everyone would be about 150 or 160 exajoules. Or on a per capita basis, this is about 17 gigajoules per capita, and this is dominated by mobility. And also health, shelter, and nutrition are significant portions of this, but it's much lower than the current average, about 55 gigajoules per capita of energy use. But while we start from a universal definition of decent living standards, so everyone has the same definition, for instance, of comfortable levels of heating and cooling, the heating and cooling needs and the energy needs for that are different. And it might be current infrastructures, it might be because of different climate, might be different diet. So there are a couple of these different aspects that we take into account for each country. And that leads to a variation of the energy needs for the same human needs from about 9 to 36 gigajoules per capita per year. So quite some variation. But as I write on the previous slide, this variation is about of the order of 30 gigajoules per capita. The total inequality and total energy use that we're having right now is much bigger, right? So in the Northern American region, all the way on the left, energy use per capita is well above 150 gigajoules per capita per person. And it strikes us also that the inequality in total energy use is about the same as the inequality as the estimated inequality in just basic energy needs provisioning. So also at the basic level, there is a lot of inequality. And this is international inequality. And so zooming in then on the energy gaps, so the extra energy that's required to provide to a person, to people, and what effect that would have on regions. That is, of course, different per region. So here, the biggest gaps are definitely in sub-Saharan Africa, where the gap is even bigger than the currently estimated energy provided for decent living. And the gap differs per region, but this is just for the regions that I'm plotting here is just the global south. Knowing all of that, knowing these gaps, we can start thinking about scenarios. So no climate policy scenarios generally grow energy demand, and to meet certain climate targets, because very fast decarbonization is required, energy demand is generally pushed down. Basic energy needs need to grow, but they don't grow as much that they actually become higher, right? So it's this 150, 160 exajoules, and 1.5 degree compatible pathways still stay about at 400 exajoules. So there is still some headroom, but this is on a global level. So we also should start moving to a perspective of more regional level. And here we have 5 different regions that are used by the IPCC. And you can see over time, going from 2020 to 2050, that this share that is required for just providing decent living indeed increases, but it never goes higher than 50%. So the affluence share, the room for inequality, you could also say, is still there. Yeah, so generally less than 50%. And this holds also under strong climate mitigation. So that's the lighter shaded region. So the difficult challenge you start really seeing if you move to a country level. So this is just sub-Saharan African countries, and on the left side you see historical final energy per capita, and basically what you can see is that total energy growth has not outpaced population growth. So most countries actually stay relatively stable in sub-Saharan Africa with their current energy consumption. To go towards providing decent living energy for everyone, you do need strong growth. So for some countries, DLE is actually, so decent living energy is actually multiple times higher than their current total energy use. We also did a very quick, very dirty analysis on just a correlation across a cross-sectional correlation with GDP. And that indicates that if trends would just continue with growing GDP, that doesn't work. yeah, so going to my last slide then, the use of this for modeling. So firstly, it could be a useful way for accounting inequality in scenarios by integrating this perspective of how much energy and tracking how much energy is used in your scenarios for just providing basic needs. That could be one way to make this useful. A second way would be to identify demand side mitigation potential within the model as well. So if for a certain sector or for a certain region, the total energy is much higher than the basic energy needs, that could indicate some mitigation potential. It's also multidimensional, so it's going beyond monetary or GDP-derived indicators, and the concept can, in principle, be expanded to other resources beyond energy. Yeah, if you want to have a bit more of a look, the paper was published a few months ago, and then we'll move on to questions and discussion, I think. Thanks.
Kai, you have a question.
Yes, thanks, Jarmo. It's a very interesting presentation. Very interesting work as well. But you mentioned it very briefly at the end. But I was quite curious why you chose energy to focus on first and not, for example, money. I mean, if you need to build an extra house, then that costs energy, sure, but it also costs materials and money and place and these kind of stuff. So why did you choose energy, and what do you think that also will be expanded shortly?
Shortly, I don't know. It's quite some work to do this podcast work. But yeah, I mean, energy. I guess it was so logical from sitting here in the energy department. But basically, energy is required for human development. We notice if you expand provisioning in general, also energy consumption goes up. Same time, if you provide electricity access, more development is possible. So energy has a strong connection to energy to development. Second, from second side, it also has a very strong connection to climate change. So it's from the emission side, energy production is huge, right? So identifying the potential reduction of energy here, basically energy is seen as the link, as an obvious link for us between development and climate change, so environmental impacts and development. Yeah.
Okay, thanks.
Sarita, you have a question as well.
I had a question about the range, basically between regions. The South Asia versus Sub-Saharan Africa. I was quite surprised that the South Asian region has a much lower range for decent living. When you see the climatic conditions and compare it with Africa, it would be almost the same. And we've seen models where it's on a higher range. So from an aspiration perspective, when you talk about decent living, shouldn't it be equal when we are talking about region, looking at the climate and other things, especially materials as well?
Yeah, thanks a lot. That's a great question. Indeed, climatic impact is one thing. The other part that plays a role in determining this share and how we have worked with it is the modal shares of transport. So if the modal shares of transport in the starting base are already different, then that means also different basic energy need. And we assume some convergence, basically in global north countries that have a really high share of private transport, we let them come back and basically reduce that to not overstate this importance there. But transport modal shares are one impact here. And so climate is an impact. I would not be able to say on top of my head whether it is significant between Sub-Saharan Africa and South Asia, because definitely heating basic energy needs in general are higher than cooling. So this explains in part why in Sub-Saharan Africa and South Asia both are relatively low. One other aspect, but that would be small, would be nutrition, maybe a difference in diets, but I cannot see that being a very big difference. So I'm afraid I don't have a full answer to what the change is, because there are many different aspects, but I could get back to you on this one.
Thank you.
Thank you very much. Well, actually, it seems like the good moment for me to hand over to Sarita, the chairing of the rest of the session. So Sarita, please.
Thank you, Celine. So I would now give the floor to Toon, who would be, I think, presenting on the reconciling competitiveness and equity in EU climate policy.
Thanks for having me here. My name is Toon VANDYCK. I work for the European Commission's Joint Research Center. And so with this presentation, we'll have a more EU focus compared to the previous presentations. This is work that is based on our contribution in the Energy Modeling Forum number 36 on carbon pricing after Paris. The paper is by now published in Energy Economics, so I invite you to have a look if you are interested. And this is, of course, work together with my colleagues here in the JRC. And the main topic of the work actually is about feasibility. It's about acceptability of climate policy. And we look at two main components here. I think if we think about feasibility of climate policies, it's important to think about potential impacts for particular stakeholder groups. And two that are relevant is, on the one hand side, the energy intensive industries that may see implications on their competitiveness in case of unilateral climate policy. And another important stakeholder group is the households. And we have seen a lot of attention lately in the policy debates on the just transition and distributional impacts across households. And here we'll look a bit at the interaction between the two, so distributional impacts and the competitiveness impacts. Just as a quick intro, looking at the literature, I think there's been quite a lot of work already on the interface between climate policy and international trade, on carbon leakage, competitiveness. And there's also been already quite a lot on climate policy and distributional impacts. We saw a couple of examples in the previous presentations. And also on the interface between trade policy or international trade and inequality and poverty, there's already quite some work, but we found there was not so much on the interface of the three. So what we'll do in this presentation and what we did in this paper is to look at climate policy design elements that are introduced to preserve the competitive position of energy intensive industries, and we'll see how that affects distributional impacts within countries in the EU. A quick note on the methods we use in this paper. So we use a combination of two tools, and the first one is a computable general equilibrium model. It's the JRC version of the GEMI3 model, in which we run two scenarios and we pass on some of the outputs to a microsimulation model that's run here also in the JRC. It's the Euromod microsimulation model. The variables we pass on are the price changes, both for consumption goods and for factors. So this is labor and capital. And then, of course, also the additional tax revenue from the carbon pricing that is in these scenarios here recycled as a lump sum transferred to the households. And the two main scenarios that we look at is a comparison between a full auctioning and a partial auctioning scenario. So in the EU, the preserving the competitive position has taken the form of grandfathering permits, so partial auctioning. And so we'll be comparing these two scenarios. The full auctioning is about the 100 stylized scenario, $100 carbon price across the board, all sectors covered. We only look at CO2 here, but the main distinction here is between the full and the partial auctioning. And then I will also show later three sensitivities that develop around the indexation of social transfers, pensions, unemployment benefits, etc. But the base case does not consider indexation. And then we have two variants that look at wage-based indexation or consumer price index-based indexation. And we look at 11 EU countries. I will focus here, given the time constraint, mainly on one country, but I will refer you to the paper if you're interested to compare how it looks across different countries. Now, just focusing on the key results here, I will illustrate the insights with the German results, and I'll try to go step by step in the explanation. So here we see the in the figure the welfare impacts by income deciles for 10 income deciles on the horizontal axis, and on the vertical axis we see the welfare impact as a % of income before tax recycling. This line that's shown now is the full auctioning and the no indexation case, which we see has a somewhat regressive pattern. Now, if we then compare with a partial auctioning scenario, we see actually it's slightly more regressive, and there's a number of reasons for that. One, probably the primary reason, is that to keep the same number of emission reductions in this scenario, so we give the permits for free to industry, this boosts their output, and GDP, well, for these sectors at least, output can go up, and to maintain the greenhouse gas emissions at the same level, we need a slightly higher carbon price. So this means higher prices for energy, also for households, and this gives rise to a more regressive pattern. Of course, this effect mainly occurs if the carbon permit scheme is comprehensive in covering industries and households under the same system. A second channel we see here is also the income side, so the labor and capital income that goes in the same direction. And what is not shown here is the lump sum transfer recycling. So under the partial auctioning scenario, there is typically less revenue, so there's also less room to offset the regressive effect. So actually the equity competitiveness trade-off, we find it comes through 3 channels. So the income, the expenditure, and the revenue side. And we see it occurs for all the indexation cases. So we find this equity competitiveness trade-off across the scenarios. And yeah, here the key message is that ensuring competitiveness through free permits may have may come at an equity penalty for within country income distribution. Then that's one key message. It's also insightful to look at the results across the different indexation cases, so indexation of the social benefits. So here we do a breakdown in that respect. And so we see the effects of the interactions with the social benefit system. In the EU, different countries have different systems. Some are wage-based, some are price-based, others are mixed. Generally, what we find is that a consumer price index-based indexation gives a less regressive pattern. Prices go up, and so if also unemployment rate, unemployment benefits and pensions go up, we see a less regressive pattern, and the wages go down. So this gives you a slightly more regressive pattern. The same occurs also in the partial auctioning scenario, and all in all, this gives us a set of 6 scenarios. And I think it's interesting to see that already we have quite a span of results just looking at this policy design and its interactions with the social benefit system. With the red line, the wage indexation partial auctioning being quite regressive, and the CPI-based indexation full auctioning being largely flat for the first 7-8 income deciles. The results after the lump sum recycling are progressive for all scenarios. So it shows also that this equity competitiveness trade-off, it's there, but it's not necessarily very large, such that the recycling of the revenue can still ensure a progressive outcome after transfers. Then the last slide here shows some other countries. This is just to illustrate. I will not go into detail here, but you find results for 11 countries in the paper. And to conclude, so I think we contribute to the literature by studying the interaction of competitiveness elements in climate policy design and the income distribution outcome of climate policy. And we identify this equity competitiveness trade-off. And this actually gives an extra argument in favor of auctioning permits, this time not in terms of efficiency, but in terms of equity. We also see that the indexation interaction with the social benefit system, it flattens or it mitigates the regressive impacts. It doesn't necessarily offset them. So this is not as strong as we have seen in recent papers for the US, but still it indicates that it's an important element to consider. I think my time is more or less up. So thanks a lot, and I welcome any questions you may have.
Maybe I'll just move to, for the sake of time, to the next presentation. So I would request Rebecca.
Hello, everyone. I'm Rebecca. I'm a doctoral student from COPPE UFRJ and a researcher at the Cenergia lab. And today I will present you an work in progress entitled Just Transition Pathways regarding oil quality distribution through the lens of the COPPE model. So a brief introduction here is that shrinking fossil fuels production is one of the greatest strategies to limiting climate change, but this is not so simple, since several projects already in operation can become stranded assets, and it also impacts the revenues of several countries. Crude oil is essential for oil products associated with hard-to-abate sectors such as aviation and shipping. And also the non-energetic products are fundamental for the current economy. Even in a context of energy transition, we depend on the petrochemical derived materials. So the research problem we claim here is that crude oil is the primary energy source that we mostly depend on, but is the source that more neglected by the integrated assessment models. And this table summarizes some IAMs and their oil characteristics. And as you can see, IAMs consider refining process in their frameworks, but it is not in a very detailed manner. So they have low resolution in oil qualities, refining schemes, and oil products. And besides, oil qualities directly impact the refining yields, and consequently, it affects the model choice and optimization. So this study aims to test the hypothesis that crude oil qualities and refining schemes impacting the model response in deep decarbonization scenarios. And for that, we improve the modeling of the oil sector in the COPPE model to have new insights in the topics of just transition. About the methodology, I've already presented in the last IMC Congress in a poster section, but to briefly summarize here, my initial target was to disaggregate the conventional oil categories from COPPE into 4 oil typologies: light, medium sweet, medium sour, and heavy, using the USDS database. So this is our new oil supply cost curve, considering different oil qualities where the unconventional oils are predominant, but considering the conventional oil, light and medium sour, present a larger volume of the resource. And to update the refinery database, we consider these 3 types of existing refineries using the oil and gas journal database. And we also have implemented 2 types of expansion refineries. Then we use the CIRED refining model to calculate new yields considering crude streams of different oil qualities and different refinery schemes for each one of the 18 regions in COPPE. So after getting and treating all the data, we implemented these new inputs in COPPE, creating an oil module. And the trade improvement is still in progress, but it was presented by Eduardo in a poster section yesterday. So you can search for this later for a better explanation. And now I will show some results where we compare the model response by turning on and turning off the oil model of coffee. So this is a well below 2 degree scenario, considering a budget of 600 gigatons of CO2. And as we can see, the global use of oil resource decreased 9% when considering oil qualities and refinery scams. And it also affects the oil trade between regions. So there is a significant increase in the international crude oil markets due to required exchange for oils of better quality, like light and medium sweet oils, for example. And regarding the regional trends, there are some highlights here, like a relevant decrease in the Middle East oil production. We also see a decrease in Russia and former Soviet states, and a significant increase in Africa production and also in Europe. So these regional trends bring critical implications for the oil geopolitics, so, and also for a just transition discussion when considering countries whose economy heavily depend on the revenues generated by this energy source. And the decrease in oil production leads to an increase of 150 gigabarrels of oil in the global stranded oil resource. And it means that 69% of the oil resource must remain on the ground to keep the global warming well below 2 degrees. And this behavior is mainly due to the disaggregated oil categories. So as you can see, there is a preference for light oils, and the regions with large volumes of heavy and sour crudes like Middle East and Russia and the USA are the most negatively impacted. Otherwise, Africa appears as the most positively impacted region. And the refining results show a preference for high-con refineries that have greater complexity. And despite having higher costs, their high-con refineries provide higher flexibility than the cracking schemes, allowing higher oil products ranges. And besides, by turning on the oil model, coffee use lower refinery capacity in all time steps, and we see that an increase or the maintenance of the average utilization factor. So this result means that the model is making a better use of the refineries with these modifications. And finally, as final remarks, we understand that oil is too relevant in the energy sector to not have oil qualities and refinery flexibilities well represented by the IAMs, and incorporating oil quality alters producing and consuming regions, and consequently it alters the stranded resource, and this affects countries' revenues and the just transition. The reserves and refineries already in the development have a great chance to become stranded assets, harming the regions that already made those investments. And for that reason, adaptation strategies for the refining sector as co-process with biomass and the non-energy use of oil need to be better assessed. These issues were explained in other presentations of our group, and we are willing to improve them too. And that's what I have to show you today, and thank you.
Thank you, Rebecca. So when we talk about the refineries and stranded assets, how about increasing the refining capacity? Till when do you think the oil refineries can be used because of the 2 degree and 1.5 degree, and after which they become stranded assets? Because I see that there's an increase in the African region. Do the refining capacity in African region, are they used to the full capacity or efficiently? So from that perspective.
So as we saw the results, I think the main change was about the oil qualities, because Africa has a lot of light oil qualities. So and light oils are better. We can put in the refineries, and the refineries work well with oils of better qualities. So the regions that have heavy oils and non-conventional oils is more difficult for the refineries to incorporate this type of oil. So Africa appears as having better results because of the light oils, and also like Europe appears too because of that type of oil.
Okay, so I have Alexander who has raised the hands. Please.
Just adding something to the answer of Rebecca. I'm also another author of this study. Actually, Africa does not expand a lot its refineries. It becomes mostly a crude oil exporter because of the quality, and also because of the position of Africa between Southeast Asia and the Atlantic Basin. And again, most of the refiners increased in Southeast Asia. So we have a small increase of refineries in Southeast Asia because of this mitigation scenario. And these refineries depends on better quality oils, and Africa crudes are good quality oils. So that's the main answer for your question.
Okay.
Thank you, Alexandre.
Yeah. Could I just have a follow-up, and then I'll give it to Pietro. On the follow-up is, so if it is going to Southeast Asia, is it because the usage is there? Because there would be a transportation costs as well. Is that added to the model, like the transportation of the crude to where the refining capacity is, and then again to where it is used again to another region or nation? Is that used in the model?
So like I said, we are improving the trade yet. So, but we are considering all the costs in this version that I presented. We consider costs of trade, but we are improving them using bilateral shipping trade. So I think it will be better in the future.
Okay.
And also complementing, we have also constraints on the choke points for the transportation of oil. So the model now can seize the constraints related to trade because of the choke points. And this is a major issue. But again, the trade increase in the decarbonization scenario because of this quality issue.
Thank you, Alexander and Rebecca. I'll ask Pietro to ask his question. Please, Pietro.
Yeah, I think more or less on the same points you made, but possibly another angle, so always related to trade. I was wondering if you have, so you basically increase the resolution and the quality of the representation of the oil sector, and as a consequence, trade increase because you see more the dynamic between different levels and quality of oils. I was wondering if you want to take into account somehow, and if so, how, the fact that, of course, being oil highly, let's say, a commodity that has very high geopolitical implications, if you want to take somehow into consideration the fact, of course, that must be probably scenario dependent, not hard modeling per se, the fact that some regions may or may not decide to boost their own production regardless of quality, because that could be a factor to take into consideration, for example, for the US shale or the oil sands in Canada, because of sovereignty issues mainly.
So I don't know if I understand your question, but I think the quality issues, I think it's important to work with the quality issues, but this is not when we consider just transition, it's a suboptimal result for the model. And when it's obvious that if we consider oil qualities, there are regions that will be prejudiced by that. So I don't know if I answer your question well.
If I can help you or complement you. Yeah, Pietro, we can do that in the model. And this is the history of petroleum, of the petroleum industry, the case of vulnerability and dependency, and there are some in the history of the petroleum industry. For example, in the case of the US refineries, they had invested in complexity to deal with Mexican oils, Canadian oils, and so on. And in our runs, in the runs of Rebecca of this study, we did not depict this issue, but we can do that. And by doing that, maybe, certainly, we are going to see a higher cost, given the problem of the energy dependency and this energy policy related to that, because some of the refiners should be improved to deal, for example, with Canadian crudes. The Canadian crudes that they have and sour crude oils. If you want to have them with this smaller supply of oil because of the deep decarbonization scenario, then we have to face investments in the oil refineries to deal with that. And these are not the least cost solution, but these can be justified because of energy dependence issues and so on.
Thank you.
Celine, please ask your question.
Yeah, well, it's not a question to one of the presenter, but rather a general reflection that can be addressed to all of them. I was thinking that, I mean, usually some economists, or the more classical economists, let's say, if I simplify a lot, what they would say is that, well, when looking at policies and climate policy in particular, you have two things that you can separate: the efficiency of the policy and the equity of the policy. And what you should do is look for policies that are efficient, and then you can deal with all the equity issue with ex post redistribution and transfers. And we know transfers are politically difficult to implement, especially between countries. And that is one first answer to those very classical economists. They are more nuanced than what I'm saying, but let's say. And I was wondering whether in your analysis there is something more about why in what you studied there are some reasons why you can't really separate the efficiency and the equity issue and deal with redistribution ex post, that we could answer to economists.
My answer will be based on my presentation then, and so perhaps not so much from an economist perspective, but I would say it depends on what you measure. So if we measure everything in money, and then money has a certain metric, because we need one metric to balance these two aspects, right? So the equity aspect and and the efficiency aspect, if you want to put them on the same scale, more or less, you probably also want eventually to look at one or a few metrics. But if this metric is, let's say, PPP based income measure, it's only one aspect perhaps. So we at least see in our work that a poverty line does not, I mean, it strongly correlates, of course, with provisioning of decent living standards, but it's not ideal. There are variations between countries comparing the poverty headcount with the decent living standards deprivation. And at the same time, let's say even a $5.50 a day poverty headcount doesn't actually ensure providing most of these services. So life is more multidimensional, and for instance, healthcare is very difficult to capture in household income, because healthcare provisioning might be free in some countries, or it might be super expensive, as it might be in the US. So measuring the right things when it comes to equity is also important.
Robin, please go ahead.
Well, since there's no other questions, I guess I'll follow up on Jarmo's point there. If there is a discrepancy between what people are actually spending money on and the amount of money they have, doesn't that, with the exception of healthcare, doesn't that generally just indicate that their preferences are just not the ones you assume that they have? And so, like, to what extent is it like the responsibility of the modeler to work out what everyone's preferences should be?
Yeah, I think that's a very good point, and it also separates, of course, the approach I took here and presented here, which is not preference based actually, and the approach that I think many classical economists have used, which is basically the preferences are basically revealed by indeed how people spend their money. So I think that those are two different approaches to dealing with or analyzing inequality. So that's definitely a discrepancy also in the methods that you use to analyze it. And yeah, I think both approaches can be used. Yeah, so that would be my answer, I think.
Yeah.
Thank you.
Thank you. Thank you, Robin. Thank you, Jarmo.